Join the conversation.
You're with Cape Talk.
And since we taken the naked scientist into a classroom today, of course, those questions are going to come from within that classroom. Hence, your questions that you've already sent to us will not be answered today, but we'll hold it over to next Friday. But another last Friday of the month, so it's time for the naked scientist. Of course, Dr. Chris Smith, Chair of Science at the University of Cambridge, joining us on the line. And then the lovely kids from Para East Primary also joining us this week. A mix of grade 4 and grade 7 learners, I believe, and grade 7 educator, Mrs. Lee Lombard will guide us through the segment. Welcome to Cape Town, Cape Talk, Miss Lombard.
Good morning. How are you?
Apart from being a little tongue-tied this morning for whatever reason, absolutely wonderful. You know, Friday makes me happy, but clearly the tongue is relaxing already. So just tell us about the setting that you are in. I believe there's a lot of excited young people looking to interact with the naked scientist.
Yes, most definitely. I think, first of all, we're all just so excited. Our kids are done with their final tests for the year. And obviously, it's Friday, so there's already so much excitement. And then added to that, the Naked Scientist Initiative. Yeah, the kids are beside themselves and waiting with their questions.
Maybe I should just go to Dr. Chris Smith to also say hello to all the kids and the teachers that are waiting in anticipation.
They've done their test. I've got mine coming today. I wait with trepidation.
Definitely.
Okay, so they're going to be asking the questions. Let's hope, I have no doubt, the naked scientist will be able to answer. So guide us through it. Introduce us to the learners and let them ask their questions, Mrs. Lombard.
Okay, so I think we're going to do the test one question at a time. First up, we have Gabriella Isaacs. She's a grade 4 learner and she is going to ask Dr. Smith her question. Are you ready, sir?
I'm ready.
Okay, Gabriella.
Okay. Will we see the next comments?
The next comet, I think I heard.
Okay. Well, hello, Gabriella. The answer is that there are many, many comets. Comets are what we call dirty ice balls. They are lumps of ice and muck and debris left over from when the solar system, which is the sun and our clutch of planets, were forming about 5 billion years ago. And many of them are out in very deep space and they're on really long orbits. If you imagine a circle and you squash it so it becomes an ellipse, some of them are on these really long elliptical orbits which carries them far out into the solar system and then they periodically come back past. But there are lots of them. Some of them we have documented in the past, like Halley's Comet, for example. Some are on such long orbits that we see them only transiently for a glimpse of, about a month or two, and then for the rest of our lifetimes they will never come back. So it really depends, and there's lots of them, but some of them we're going to see fairly frequently and some of them we're only going to see once in our lifetime. Some of them are so far out in space that we're not going to see them, but our children's children may see them. So it really depends on which comet you're talking about, but there are lots of them.
Thank you, sir. It's quite interesting. My kids are overwhelmed with the information. Can Gabriella ask you another question? She's quite a little scientist.
I don't see why not, since she was the first up. Someone has to go first, so there's got to be a payback.
Okay. What is after the Milky Way galaxy?
Well, Gabriella, the answer is that if you take a step back and imagine you could see the whole universe that we're in, stepping back and looking at the whole universe, which you can't do because the universe is everywhere, the universe is everything, what you would see is our Milky Way, which is a spiral-shaped galaxy, and in there is something like a couple of 100 billion stars. And if you were to then look elsewhere, you'd see that there was 100 or 200 billion more galaxies like the Milky Way elsewhere in the universe. Some a bit closer to us, some farther away, but the distances are absolutely vast. You're talking years and years of time that it takes light to travel through space. You know how fast light goes. So there are billions and billions of galaxies out there. Some of them are shaped like ours. Some of them have slightly different shapes. Some of them have more stars. Some of them have slightly fewer. But there are a lot of them.
Thank you.
Okay. Next up, we have Connor, who's also a grade 4 learner, and he is standing ready with his question, Dr. Smith.
Hello, Connor.
Hello, Dr. Smith. Question 1. What year was a monkey sent into space?
I don't know about monkeys, but I know that the first animal in space was actually a dog. The first animal to orbit. The Russians did this with the Russian space program, and the dog was called Laika. And this was before Yuri Gagarin, who was the first man in space, made his amazing orbit. And so they did experiments on monkeys after they did the dogs, but I don't know exactly what year that would be. It would presumably be late 50s, early 60s that they were doing all this work. So it would be more than 50 years ago now.
That's very cool. Thanks. Can I ask another question?
If you're quick.
Which was created first, the moon or Earth?
Well, the moon definitely came along after the Earth. And we know the Earth is about 5 billion years old, and the moon formed about 4.5 billion years ago. And the way we think that happened is that the Earth and another planet ended up colliding in space. And the other planet was probably about the same size as Mars, so a bit smaller than the Earth, and they smacked into each other. And when that happened, the two planets joined together, but a lot of the material that was the surface of the Earth was thrown up into space, and the Earth's gravity held onto it and slowly made it collect and coalesce together into a ball like we have now, the moon. And this is why the Earth has a moon which is so big compared to our planet. Most planets in the solar system are very big and they have small moons. The Earth is unusual in having such a giant moon, and this is because we probably produced our moon after the Earth had formed from a collision with another planet.
You're so smart. Thank you.
You're welcome. Good question. Who's next?
Dr. Smith, next we have Yovi Hudsonberg, also a grade 4 learner, and she's standing ready with her question.
What have you got for us? Good morning.
What lifts up the moon?
What lifts up the moon? I think that was the question. Well, the answer is that the moon is held by the Earth because any object which has mass, in other words, it weighs something, will attract any other object. This is called gravity. And it was the insight, first of all, of the scientist Isaac Newton in Cambridge a few hundred years ago. There is this story that he was sitting under an apple tree at Trinity College and an apple fell on his head. And it made him think, well, why does anything fall downwards? And that was his insights into this idea of gravity. But the moon exists next door to the Earth, with the Earth pulling on the moon and the moon pulling on the Earth, and the two attracting each other. It's rather like you and a partner holding hands and then swinging round in a dance, and there's a pull on your two hands holding each other, and if you were to let go, each of you would fly off in opposite directions. Well, the Earth is holding onto the moon with gravity, and the moon is holding onto the Earth with gravity. There's nothing lifting up the moon. The moon is going in a big circle around the Earth, and if you were to let go, the moon would fly off into space. So we are holding onto it, not pushing it up there.
Thank you for answering my question, Dr.
You're
Smith.
welcome. Good question.
Next up, Dr. Smith, we have Tandor Daniel, also a grade 4 learner.
Hello, Tandor. You've got some bright kids in this class. Goodness, I'm getting a run for my money this morning.
Definitely.
What would you like to know, Tandor?
What is the dent on the moon called?
The dents. The moon is covered in craters. And this is because the moon has, over its history, I said it was about 4.57 billion, so 4,570 million years old. That's the age of the moon. The moon has been up there a long time. And when the Earth was young, way back about 4.5 to 5 billion years ago, the solar system was full of debris and material that was what was producing planets at the time. And so there was an enormous number of impacts on the Earth and on the moon by asteroids and comets, which were raining in on us. There was a period about 4 billion years ago. We call it the Late Heavy Bombardment. And this is when material smashed into the planet on a regular basis. And so the moon got covered in these impact craters. And because the moon doesn't have volcanoes in the same way that the Earth does, many of them remain. The reason that we don't have lots of craters left on the Earth from this happening is because we have tectonic plates and volcanoes, and so the Earth's surface is relatively young. There are some parts of the Earth's surface which are still a vestige of the early history of the Earth. Some of the oldest rocks on Earth are in Australia, in Western Australia, and in Southern Africa. And they go back billions of years. But on the whole, most of the Earth's surface has been recovered or recoated by lava from volcanoes. the moon had very limited volcanism because it doesn't have the same structure as the Earth, and therefore what was on the surface of the moon remained on the surface of the Earth, of the moon. So those dents and craters that you see are a legacy of the moon having been hit and collided with by lots of impactors over its 4.5 billion year lifetime.
Now I know why the moon looks like cheese.
That's
Thank
right.
you, sir.
That's right. You're very welcome. And that's why we think there's a face in the moon. People say that's the man in the moon, because if you look at something the right way, you can always see a face in anything. And if you look at the shape of an arrangement of those dark patches, which are the craters, they do, in some circumstances, look a bit like a face.
I think we're definitely going to have to put that in one of our science tests next year. Thank you, Dr. Smith. Next up, we have Pamela Bungu, also a grade 4 learner.
Hello,
Morning,
Pamela.
Dr. Smith.
Good morning.
Morning. How are you today?
I'm very good. How are you?
My first question is, how was the moon created?
Well, we did sort of cover that earlier because I mentioned that the moon was the product of a giant collision in space. We call the planet that caused it to form Theia. People thought that was a nice name. And so a planet the size of Mars ran into the Earth, and the cores of the two planets merged together, but the crust material from the Earth, in other words, the stuff we walk around on, was thrown up into space. And it would have formed a big kind of cloud or blanket round the Earth, blotting out the sun for millions of years. But slowly, because of gravity, and gravity making things attract each other, in the same way that the solar system, with all the planets around the sun, formed from a whole lot of dust and gas around the early sun, the dust and gas around the Earth formed by that collision would have slowly coalesced to give us the moon. And in the early days, the moon was much closer to the Earth. It was going round much more quickly, so an orbit time for the moon would have been much shorter, and that meant we would have had very big tides. High tides on Earth then would be much higher than they were today, but the Earth is losing some of its spin to the moon for various reasons. So the Earth is slowing down its turning a bit, and the moon is getting some of that energy, and this means the moon is moving about 2 centimetres further away from the Earth every single year. And we know this because when the Apollo missions went to the moon, they put a mirror on the moon surface, and every day they're bouncing a laser beam from the Earth onto the mirror and back again, and we can measure how long the light takes to make that journey. And because the speed of light is constant, if you know how long something travelling at a constant speed took to make the trip, you can work out how far it is to the thing that it came from. And so you can calculate that the moon is moving a couple of centimetres farther from the Earth every year, which is why slowly over time the moon will get farther and farther away from us and tides will get smaller and smaller. But don't worry, this is not going to happen anytime soon. In our lifetimes, the moon will remain pretty much where it is, and over the course of millions of years, eventually it will get a bit further away.
Thank you, Dr. Smith. Now I know what the moon is made of.
And it's not cheese either.
Okay.
Dr. Smith, I am going to hand over to a grade 7 learner who often likes to pick our teachers' brains in the class and always puts us up to a challenge. I'm going to introduce you to Mohammed Ayez Snyders, and he's going to ask you one question, and then I'll hand back to the grade 4 learners.
Hello,
Good morning,
Mohammed.
sir.
Good morning. How are you?
I'm good, and you? I would actually like to know how scientists would be able to calculate how old the Earth is.
Right. Well, yes, because I confidently said the Earth's about 5 billion years old, didn't I? So how would we know that? Well, the answer is there are lots of clocks that we can use that are written into things. And one of the best ones when you're dealing with things that are really, really old is a radioactive clock. There are chemicals on Earth which exist in forms that make them radioactive. And what that means is that the chemical, the element, is unstable. The atoms inside have a structure that means that they don't hold together very well, and so they fall apart. And when the atom splits apart, it spits out some radiation, and it divides into smaller, what are called daughter nuclides. And those daughters are like, if I split myself in two, I would have two things that together were half my weight. In fact, it's slightly less than half because some of the radiation has been given off. But basically, you have an atom that splits into two daughters, and you know what those daughters are. You know what the new chemicals are. So if you work out how much of one thing there is relative to another, you can, because this happens at a constant rate, you can work out how many of those processes must have happened over how many years, and therefore how long that process has been going on in that particular sample you've got. So one of the radioactive chemicals, called uranium, for example, turns into another chemical called lead. And if you look at the amounts of these things in different substances, you can work out how long they must have been together in that sample for the certain ratio of one to turn into another. And because the time it takes that process to happen is millions of years, then you've got something which is a clock ticking very slowly and very reliably over a really long time. And you can back calculate how old then must the Earth be. And that's one way of doing this. And that's what scientists do to work out the ages of rocks and things like that, and then work out how old they must be with some degree of variation when you're dealing with things like the Earth, bits of rock that come in from space, for example. And that's how we do it.
Thank you, sir. That was very informative.
Okay, next up we have Kiana, a grade 4 learner at our school, Para East Primary. She's standing by with her question.
Hello, Kiana. How are you?
I'm fine, thank you. Yourself, sir?
I'm very good. Are you a keen scientist?
Excuse me?
Are you a keen scientist?
Yes, kind of.
I hope we're going to make you even keener today. What would you like to ask?
My first question are, why are Neptune and Uranus blue?
Well, they're not really blue. They just look a bit blue. And we tend to paint them blue to make them look nice in pictures of the solar system. They are what we call gas giant planets. They do have some colour, but the gas that they're mostly made of is hydrogen, but there are some other things in there as well. They get their colour from the fact that when we shine light on things, every substance, every chemical that we know about absorbs and also gives off light of different colours. And this is how we can tell what things are made of. So if we look at the sun, for example, no one has ever been to the sun, but we know what chemicals are in the sun because we can look at the colours of light coming from the sun. This is called spectroscopy. And one of the people who invented it, have you ever used a Bunsen burner, one of the things that you see in the science lab that you light it and it makes a flame and you heat things with it? The guy who invented that also came up with the science of spectroscopy, the idea that different chemicals produce light of different colours. And so if you look at the combination of light coming from something, you can work out what must be in that thing. And if we look at different planets in the solar system, we can work out, based on the light coming back from them, some of the chemicals that are there and in what sorts of proportions. And so we know what these planets are made of, but they're not naturally a deep blue or a deep green colour. That makes the drawings we make look pretty, but they do have some colour, and those colours are because of the gases and the composition of the atmosphere. But those planets are huge, and they're mostly made of gases like hydrogen. And they formed a long time ago in the earliest part of the solar system, hoovered up lots of gas, and then migrated to where they now are, out in deep space. It's a long way out to those planets. You'd be very old if you got in a rocket to go out there and then hang around out there for a long time. It'd take a very long time to get to them.
The Naked Scientist, the kids edition. We've taken the Naked Scientist, Chris Smith, also the chair of science at the University of Cambridge, into Parow East Primary School, where grade 7 educator Mrs. Lee Lomberg is kind of rallying the classes there to ask questions. Mrs. Lomberg, back to you. Who's next?
Next up is Zoe Lee. She's a grade 7 learner, one of our top academic achievers at the school, I'm proud to say. And I'm proud to say that I'm also one of her educators. So I'm going to let her ask Dr. Smith her question.
Hi, Zoe.
My question for you is, why is the sun the only star that can be seen during the daytime?
Well, the reason is it's all relative. The sun is very close to us. It's our nearest star. And obviously, we wouldn't be here without it, because all of the energy we get to play with here on Earth, give or take, is arriving from the sun in the form of light. And it keeps us warm. The other stars that you can see, putting to one side the planets, because although we talk about stars in the night sky, not all the stars you can see are stars like the sun. There are planets there as well, of course, but they're just a handful of stars. So we put those to one side. The rest of those stars out there in the night sky are a long, long way away. They are light years away. In other words, it takes light travelling at the speed that light travels, 300,000 kilometres every second. It takes light years from those stars to get to us. And because light, as it's travelling through space, is spreading out, the light that started a lot of it in one place where that star is, by the time it gets to where we are over a massive distance, the light has spread out a lot. So very few rays reach us compared to the number that were leaving that star. So when it's a bright day, if you look up into the sky, you're seeing enormous amounts of light coming to us from our own sun, our star. But the tiny pinprick of light, the few rays of light that are coming from those very distant stars, is so weak in comparison that you can't see them. It's a bit like if you were to go into a noisy place, the sound would drown out someone who is whispering next to you. And those stars far away are like the person whispering, and the big loud sounds are like the noise in the noisy place from our sun. So it's all relative. They are there, but you find them much harder to see during the day because their light is much weaker than the enormous amount of light that's flooding into our eyes from our own sun that's much closer.
Thank you for answering my question. I hope you have a lovely day further.
And you?
Then Dr. Smith, I'm going to introduce you to Jessie Katansi, also a grade 7 learner, and she is going to ask you her burning question.
Hi, Jessie.
Morning, sir.
Morning.
So my question is, if we were to get stuck in a black hole, how fast would we have to move to get out of it?
Well, Jessie, you can't get out of it. And that's the problem. As far as we know, nothing can get out of a black hole. The gravity pulling things into a black hole is so powerful that not even light can escape. Now, light doesn't have any mass. In other words, if you were to put light, the particles of light, we call them photons, on a weighing scale, they wouldn't weigh anything. So even light can't get out of a black hole despite not weighing anything. We all weigh something, we have mass, and therefore the amount of energy we would need would be enormously great compared to what light takes. And if light can't get out, then there's no chance, no hope for us. So we believe, based on our current understanding of the physics, that if you cross something that's called the event horizon, which is the point of no return at the mouth of a black hole, once you go in there, there's no going back. And after that, you would become stretched out, subject to a very intense, very powerful gravitational field that would, as some scientists have dubbed it, spaghettify you quite quickly.
Okay, sir. Thank you for answering my question. Have a lovely day.
And you, so don't
Thank
go in
you.
any black holes anytime soon.
I'll make
Mrs.
sure not
Lombard,
to.
Yes.
we are running out of time, so I'm just trying to manage the time if you don't mind. We have an opportunity for a last question. Should it be Vanella's question, maybe?
Yes, I was thinking the same, Vanilla. I'm going to introduce you to Vanilla. She is a grade 7 learner at our Parry East Primary School. Vanilla, you can take over.
Good morning, sir.
Morning, Vanilla. What would you like to ask?
Today I would like to ask, since the universe is a very big place, I would like to ask, are there any other life forces out there?
Well, Vanilla, we think that given how many stars there are, I said to one of the earlier questions, I said there's about 100 to 200 billion stars in our galaxy, and there's a couple of 100 billion galaxies probably. So that means you've got 1 followed by 22 zeros, stars in the universe. And if each of those stars has a handful of planets like ours, you can see that there's an enormous number of possibilities for life to exist, because the chances of there being another planet near to a star like the Sun, which is like the Earth, which is the right distance away, which has got water on it and an atmosphere to make a home from home like the Earth, the chances of that happening with that many stars out there and therefore that many planets out there is so high that scientists find it inconceivable that there aren't life processes similar to that running here on Earth elsewhere in the universe. But as you say, the universe is a really big place, so finding them, that's going to be the challenge.
Thank you, sir, for answering my question.
Thank you, Vanilla, for your question, and thank you to the wonderful people, and Shante Rowland, principal at Paddo East Primary School. Thank you for allowing the Naked Scientist in, and Lee Lomberg, of course, facilitating for this little interaction, a wonderful interaction that I have no doubt has landed well with the kids out on that side. Thank you, Dr. Chris Smith, and we'll chat again next week. It is 10 o'clock. It is time for Eyewitness News.